In this video, I'm going to be giving you a quick tutorial on how to draw free body diagrams with a couple of examples outside of the ones that we would have done in class. And I'm going to start out by running through the steps of thinking through how to draw and set up one of these to best help you during a usual like force and Newton's second law related problem. So I'm going to start out with the steps here, and I'm going to, as we go through them, elaborate a little bit more on the types of forces that you're likely to encounter in this. So in drawing a free body diagram, really the first step is to just draw some kind of shape to attach your forces to. And so you usually want something like, well, on this next slide here, we've got, I believe, just like a couple of boxes or something. You don't really have to get too fancy with it. Next is to draw and label all the external forces acting on the object. That's going to be like, if you have some boxes like this, well, you want to just assess where any sort of contact or where every sort of like push or pull is happening on this object, so that you can consider all of the possible areas. Next is really a couple of the rules regarding like specific forces. So gravitational forces are always going to be straight down. Now, gravitational force is also considered to be called weight. Now, weight is different from mass in that mass is like how much stuff an object has. It's, intrinsic to the object itself. Weight is dependent on the gravitational pull of the planet that you're on. On Earth, that gravitational pull is 9.8 meters per second squared. But on, say, the moon, that acceleration due to gravity is going to be lower, and thus the weight that you would read on a scale would be less for any given object. And so the way that you calculate this is by multiplying the mass times the acceleration due to gravity of the planet that you're on. And so on a free body diagram, because we're assuming that the object is relatively close to the surface of the planet, you want to be drawing that weight force directly downwards, always. There is never really any exception unless we're talking about orbits or something. Okay, then the next one here is going to be normal forces. And these are always perpendicular to the surfaces that the object is in contact with. The normal force gets its name from the Latin word for perpendicular. So normal really just is another way to say that this force needs to be perpendicular, always. You can do some kind of interpretive dance to remember it. And so a normal force, in other words, is generally just a contact force. It's like when you are being just still on the ground, or you're sitting on a table or a chair, or an object is doing that. The reason why gravity isn't just causing that object to plummet straight down to the center of the earth is because of the normal force. The normal force is just that object having to exert an equal and opposite force back up on you to keep you from sliding down any further. So generally, anytime an object is in contact with a surface, like this ground here, not only does the normal force need to be there, but it also needs to be perpendicular to that surface at a right angle to it. Okay? Now, frictional forces are always drawn in the direction opposing motion. Now, that means that, whatever direction this object is initially going in, or whatever direction it's trying to go in, friction force needs to be pointing the opposite way. Friction is the contrarian here. Sometimes it helps you, sometimes it doesn't. It just depends. Another thing is that friction needs to be parallel to the surfaces in contact. So as opposed to normal force, which is perpendicular, friction has got to be parallel. So it's going to be going along the surface in contact. All right, and then finally, tensile or tension forces are always drawn away from the objects that they're attached to. That's like this setup right here, where generally if you were to grab a piece of rope and you were to ask somebody to do an impromptu tug of war with that piece of string, you're going to feel like you're pulling away from them, and you're going to feel like the string is pulling away from you. It's pulling towards the person you're in the tug of war with. If you ask the person what they're feeling, they're going to be saying the exact opposite. They'll say, oh, well, I feel like the string is pulling towards you. And so it's a unique property of tension that it always just pulls away from the point of contact. And that is really all of the forces that we're going to be working with here. So I'm going to move to the packet so that we can start putting a little bit into practice here. All right, and now we're here. And so with these examples, we did a couple in class, and I'm going to highlight a few more that we are not going to cover in class, so you have some motivation to watch this. So this first one, we've got a box of mass 25 kilograms being dragged along a frictionless surface by a mysterious 45 Newton force right here. So we're going to start by just drawing a simple object. I'm really a block guy, but if you want to draw circles or dots or get really fancy with it, I'm not going to blame you. And so on this block, I like to say that really before anything else, before any forces that are even pictured, what is one force that 100% has to be acting on this block? Well, it has a mass, so odds are it has a force due to gravity acting on it. Everything with a mass has a gravitational force acting on it. And we're going to call that Fg. You could also get into the habit of going ahead and just solving for it outright right there, because it is a very easy thing to solve for at the start of a problem. All right, so next, let's go ahead and just put this force on the board. So we've got an applied force, it looks like, of 45 newtons going to the right this way. All right, and so I'm going to call that Fa, but you could also call it 45 newtons. Whoops, broke into the other box there. All right, and then finally, currently we have a net force acting on this box, but it doesn't look like it should be accelerating in the vertical direction. It's being just dragged along that frictionless surface, and the keyword there is surface. Surface implies there's got to be a normal force there. So the normal force in this case is got to be perpendicular to the surface, like this way. So let's go ahead and draw that on the block as well. All right, and besides that, there's no friction, so we don't need to consider that here. And so it looks like all of our forces are accounted for. So over here, there are a couple of questions just to elaborate on this a little bit. So the first question is asking what the net force acting on the box is. Well, we're assuming it's not accelerating vertically because it's not flying and it's not falling. So really all of the force that could be accelerating this thing is in the horizontal direction. So let's go ahead and just say, well, the net force is probably going to be about 45 newtons, considering it's not floating or falling. And in that same vein, what can we say about the sum of the vertical forces acting on the box? Well, again, it's not accelerating vertically, so we could say the sum of the forces in the y direction, so vertically, have to sum up to 0, or have to add up to 0. In other words, you could say that's going to be the same thing as saying Fn plus mg equals 0. Okay. All right. And so that's kind of a nice simple one to start out with. So we're going to start shaking things up here after this. All right, so here's a slightly spicier one. So in this case, we've got a box. It has a mass of 3.8 kilograms, and it's being pushed by two forces. Ooh, scary. So again, we're going to start with just a box. All right. And with that box, we've got a mass. So again, the first thing you should always draw is the force due to gravity acting downwards on this thing. Because again, it's got a mass, it's probably on a planet, so it probably has a gravitational force. We could also say that that force is equal to the mass times the acceleration due to gravity, which would be 3.8 times roughly 10. So we could say that that's about 38 newtons total. Okay. Now, up here, we could also say that it's in contact with a horizontal surface and it's frictionless. So if we've got an object on a surface, there needs to be a normal force perpendicular to that surface, like that. So let's go ahead and add that to our free body diagram as well. Okay. Next we've got this 68 Newton applied force, and that one's at an angle, so I'm going to try my best to sketch that. Ooh, and lest we forget, this force is being applied down and to the left, like that, into the crate. So at this point, because we're given this force and we're given an angle, we can use trig to get this thing on the same page as the other forces that are vertical and horizontal. So in this case, I'm going to draw out a horizontal component like that, and then I'm going to add this additional vertical component to finish the right triangle. And now the 60-degree angle is given on this corner of the right triangle, and our force is 68 newtons. in total. But if we want to find the components, we would say, well, this vertical component right here is 68 times sine of 60 degrees, which is roughly equal to 59 newtons. And this force over here, which is to the left, is 68 cosine 60 degrees, which is roughly equal to 34 newtons. Now, before you move on, it's important to acknowledge the directions of these, because that's pretty important. So this one is going downwards, or it's negative, and this one is going leftwards, which is also negative. That'll only be important for later. All right, and then finally, we've got one more force that's being applied to the right. It's a 34 Newton force, so let's just go ahead and tack that on right there. And we'll say it's going to the right, and that's all we need to do there. So now let's take a look at some of these questions. First, we're being asked to figure out what the direction of the box's acceleration is. Now, okay, there's a lot to consider here, but before you even jump into anything else, first acknowledge, is this box flying? No? Okay. Now, is this box plummeting through the surface of the Earth? Also probably no. If either of those conditions do not apply, then you can already safely assume that there's no acceleration in the vertical direction. So really, we're just focusing on the other direction, the x direction here. Okay? And so the sum of forces in the x direction have to equal, let's see, well, we've got a rightward force of 34 newtons over here. So we'll keep that positive. And then we've got a leftward force of 34 newtons over here. So we'll add that and say negative 34 newtons. Now, if you do the very quick mental math here to figure out what that equals, we're going to find that the horizontal forces add up to 0 newtons. That's good, because that means automatically that the acceleration in the x direction has got to equal 0 as well. Nice. All right. So then finally, considering the vertical direction here, it is asking us to figure out what the sum of the vertical forces acting on the box need to equal. Well, in this case, again, it's not falling and it's not flying. So overall, the sum of all the vertical forces needs to equal 0. Now, this is a unique opportunity to see how these would actually add up. So in this case, let's go ahead and just expand this out a little bit. So how these forces add together. We do have one upward normal force right here, so we'll just add that to the front. And then to that, we need to add 2 downward forces. So we've got first a negative 59 Newton force from that applied force. Just go ahead and keep it like that. Plus, we have another downward force due to gravity over here. So negative 38 newtons. And once we've considered all of that need to equal 0. So you could use this as an opportunity to solve for what the normal force needs to be in order to keep this whole system the way it is. But we're going to save that for another time. And finally, this is a very funky one. We've got a block on an incline. This is going to be the subject of a whole day in class, focusing on these types of problems, but it's good to know how to set them up now. So for these sorts of problems, I actually do like to include the incline as well, because it helps really get you, helps you get your bearings on where all these forces are relative to the ground below. So I'm going to do my best to draw the inclined plane as well as the block that's on it. And now we've got this crate, which has a mass m. So right off the bat, it's got a mass, right? So let's just draw a force due to gravity, still straight down, no exceptions, not even on an incline. So that's going to be Fg, and again, that's going to equal the mass times the acceleration due to gravity, which is 10 or 9.8. Now it's being pushed up this frictionless surface. Ooh, you see that key word there, surface. Now here's the weird part. In the last two examples, that surface was horizontal. So the normal force, or the perpendicular force, should have been vertical to be perpendicular to that. In this case, our surface is along this direction. So our normal force needs to still be perpendicular to that. So it's going to be this way, like that. So we need to include that on our free body diagram. Fn. Weird. All right. And now, finally, we're being pushed by some horizontal force F, which I'm going to make green. And that's just being applied directly to the box, and we always just apply those forces directly to the box as shown. So we'll keep it like that. All right. And now there's no friction, there's no other like weird tensions or anything, so this is a complete free body diagram. We are good. So this first question here over on this side is asking, what is the direction of the crate's acceleration? Well, So normally, we've been splitting things up into horizontal and vertical. In this case, you'd imagine the box would either be sliding up or sliding down the incline. And so we're going to get to this more when we get to inclined planes, but for now, we can just say generally that this box is either going to be sliding up or down the surface of the incline. Now, we don't have any more information to know whether like the force outweighs the gravity or vice versa, but we're going to keep it the way it is. And finally, what can we say about the sum of the forces perpendicular to the incline? Well, let's just ask ourselves, is it falling? Is it flying? No? No? Okay. So we're just going to say that the sum of the forces in the perpendicular direction have to equal 0 because it's not falling or flying. Now, what do I mean perpendicular and parallel? Well, this is where we get into kind of another kind of weird property of this that I'm gonna at least give you a sneak peek of now. On problems like this, what is pulling an object down the incline? Because, you know, if you put a ball or you put a block on a steep surface, it's gonna slide down. Well, gravity is doing that action, but it's not fully pointing in that direction. So on inclined plane problems, what you're going to find is that we need to split gravity into two different directions because it's doing two things. First, it's pulling the object into the surface of the incline, like that. So we're going to call that Fg perpendicular. That's what's really canceling out with normal force here. But at the same time, depending on the angle of the incline, gravity's also got to be doing a little bit of work in pulling it down the incline. And that's what we call Fg parallel. Now, I'm going to leave it at that for now and give inclined planes their own video. But for now, know that things get a little weird with splitting that one up. All right, but that's about it. And the rest of these examples we'll either do together in class or I'll leave them for you to practice before you jump into any serious quest stuff. So I hope this video was informative, and I will catch you on the next one. Peace.